So on page 345, we're going to take a look at some examples that would utilize this concept of figuring out a value of C to help us either answer a question or proceed with finding a value. So the top half of this page is kind of a free response based question where we have some information based or given to us at the top, and then we're asked some follow-up questions to kind of evaluate or analyze this information. So an evergreen nursery usually sells a certain shrub after 6 years of growth and shaping. The growth rate during those 6 years is approximated by the differential equation. Differential just means derivative. Okay, we've kind of seen the word differentiation before, which kind of highlights derivative, so that's kind of the same concept here. So if this is a derivative equation, this is representing a rate, like they told us, and it's specifically the growth rate. So maybe we want to rephrase this as the rate at which, if you're growing, that means your height is changing. So the rate at which height is changing. All right, a different way to rephrase growth rate. T is the time in years, and H is measured as the height in centimeters. We also know that the seedlings are 12 centimeters tall when planted. So notice how this information is not necessarily a derivative value. This is representing an original function value, an original function that represented height in this case. So we could represent this information as at time 0, the height of the plant is 12. All right, let's look at A. Find the value of the differential equation above when t equals 3. Using correct units, explain what this means in the context of the problem. We can do this, no problem. Okay, let's plug in 3. And a little calculating here, we'll get 9.5. Okay, so this 9.5 value came from our derivative equation, which we said represented the rate at which height is changing. So this 9.5 represents the rate at which height is changing. Okay, notice how our derivative value is positive, so the height is changing positively, meaning the height is increasing. So the rate at which height is changing. And can we do units? We would need centimeters per year. Okay, and we were particularly looking at this exact point in time. So this would be 3 years after the plant was planted. So the rate at which height is changing in centimeters per year at t equals 3 years. All right, I say that's pretty good. You could rephrase this a different way. You could say height is increasing at a rate of 9.5 centimeters per year at the 3rd year. Okay, there's different ways you can rephrase it, but as long as you have the correct context and the correct explanation, that's all that's really important. Also, make sure you use the correct units. For part B, find the equation of h of t. The height of the shrub at any year t. So notice how this is kind of asking us to work backwards, because the equation they give us is a derivative, but they want us to find the original function that represented the height. So we're going to have to work backwards from this function. Now, if we work backwards, we know in terms of an integral symbol, I'll kind of write it up here, we normally have a function and then this dx or dt or d something at the end, which is just representing that variable of integration. And this derivative symbol actually has 2 of those pieces. Notice how we have a dh and we have a dt. So what we're going to do is kind of separate the variables. I want to get any h variable perhaps on the left side and any t variable on the right. So this dt that's in the bottom of the fraction, I'm going to multiply it over to the other side. So now that I have the dh and the dt separate, oh, I forgot my t in there. Okay, now that I have them separate, I can work backwards. And we're actually going to work backwards on both sides. Okay, what you do to one side, you do to the other. Now, this dh, I know it's all by itself, but technically we have kind of that coefficient of 1 out front. So if I were to work backwards from 1 with respect to h, okay, so now my variable on this side is h. I would just have the letter h, because if I took the derivative of h with respect to h, the derivative of that would just be 1. On the right-hand side, notice how my variable is t. So I'm going to work backwards from 1.5t. I'd have to add 1 to the power, which would be 2, and then divide the coefficient by the new power. So 1.5 divided by 2 is 0.75. And if I work backwards from 5, again, my variable of integration is t, I'd have 5t. Okay, now technically we should have put a plus c on this side and a plus c on this side, but the constant on the left could be something different than the constant on the right. So if we combine the constants together, that's just going to be a new constant anyway. So you really only need to put the plus c on one side of the equation. It technically doesn't really matter. So more often than not, we just assume that it's on the right-hand side after we've solved for this h function. So if we kind of rehash the steps here, we separated the variables. That way we could work backwards on either side. Okay, one side with h's, one side with t's. Then we worked backwards, aka integrated. And somehow, I wonder if we can figure out what the c value is, because they did give us a particular point about the height of the graph, or not the graph, but the height of the shrub at a particular time. So if I were to plug in 0 for the t's, I should get out an answer of 12. So if I put in 0 for those t's, they're just going to go away, and I'm going to be left with a c value of 12. So I guess we can say that our height equation is 0.75 t squared plus 5t plus 12. Okay, so that was our first part, find an equation, which we did. Then determine how tall the shrubs are when they are sold. So we got to figure out what number are we going to plug in for the t's, which represents the time that they're sold. And I think it said at the top, an evergreen nursery usually sells a certain shrub after 6 years of growth and shaping. So it looks like we'll plug in 6. So if you take the time to plug in 6 for the t's and calculate your value, I believe we'll get 79, or not 79, 69. And if this is representing a height, we're going to need our units as centimeters. All right, so I know it's a little bit different notation that we had here because we had dh over dt instead of a prime, but whenever that happens, we do have to separate the variables because we just want to use one variable on each side to eventually get our original function in the end. We can also maybe take an approach of particle motion related to these antiderivatives. So a particle moves along the x-axis, meaning left and right, and they give us the velocity function. At time 1, its position is 4. So maybe, let's see, it's moving along the x-axis, so maybe I'll use x to represent position on the x-axis. You could use p for position. They don't really specify what you should call it, so it's completely up to you. But maybe I'll say x of 1 equals 4. All right, so let's see. What is the acceleration of the particle at time 9? So we got to think about, they give us velocity, they're asking us about acceleration. We have to think about the connection or the relationship between the two, and we've seen so far this year that acceleration is the derivative of velocity. So I'm actually want to take a derivative of this function. It would be helpful, you can leave it the way it is and go through a quotient rule. Maybe you want to rewrite it a little bit to use a power rule. For instance, I can move the square root of t up to the top and then make it 1t to the negative 1/2 power. So the derivative shortcut you use is completely up to you, however you want to utilize the function itself. So if I take a derivative, that'll be acceleration. I'll have -1/2 t to the -3/2, and maybe I'll rewrite it. I'll have -1/2, and I can rewrite this as the square root of t cubed. And they want the acceleration at 9, so let's go ahead and plug in 9 and see what we get. All right, let's see. 9 cubed, get my calculator for a second, that's going to be pretty big. 9 cubed is 729, and if I square root that, I'll get 27. All right, times 2, we'll have 54. All right, so there's my acceleration at time 9. They don't give us any units, so I guess we don't have to worry about throwing those on. All right, let's check out B. What is the position of the particle at time 9? Okay, notice how this one's different. They give us velocity and they're asking us about position. So this is technically a first derivative and they're asking us about an original function, which means we'd have to work backwards. So I need to integrate 1t to the -1/2. Okay, this time we'll have dt, that's our variable that we're gonna work backwards from. So I got to add 1 to the power, t to the 1/2, divide the coefficient by the new power, that'd give me 2, and don't forget the plus c. All right, so again, this represented velocity, and if I work backwards, that's going to be my position. I do have a piece of information about the position, and I can use that to help me figure out c. So if I plug in 1 for t, which is basically just going to give me 2, my answer should be 4. So it looks like my c value is 2. So let's go ahead and write our position function as 2t to the 1/2 plus 2. They want us to evaluate this at 9. So I'll go ahead and plug in 9. The square root of 9 is 3, times 2 is 6, plus 2 is 8. Alright, looks good. Now, I know it's not a part of the question because we're officially done, but it might be beneficial for us to kind of review some of those properties about particle motion. Notice how both of these were asking about time 9. What if I wanted to evaluate velocity at time 9? I would plug in 9 here and get 1/3. So with all of these pieces of information related to the same point in time, I wonder if we can start to kind of describe the motion of the particle. Because we have the location, we have the velocity, and we have the acceleration. So maybe we can say at time 9, the particle is located at 8 on the x-axis. We know its velocity, which is speed and direction. So traveling to the right at a rate of 1/3. Okay, so positive velocity means it's traveling to the right, and this is its rate. And notice though how acceleration is negative, which is the opposite sign of velocity. So if velocity and acceleration have opposite signs, that means the speed of the particle is slowing down. So we can also say speed is decreasing, aka running out of room, the particle is slowing down. Okay, so all this information related to the same point in time gives us a pretty clear picture as to what this particle is doing and is or where it's even located at this time 9.